Good morning, mechanical engineers. Welcome to lecture 2 in the series for machine design this semester. So per the syllabus, today we're going to talk about beams. Beams are a very important structure in machine design and in fact all kind of structural engineering. 3 types of beams. Simply supported beams, where the beam is basically supported by points at either end. Then there's the cantilevered beam, which is supported at one end only and then basically sticks out, and so all of the force and the moment caused by the overhang has to be provided by that encased or encastra end of the beam here. The cantilevered beam with an overhang, so this is what we call, this is a little sketch of that here. It's a simple supported beam with an overhang so that the load is not between the 2 supports. That's kind of the 3rd type. So these are the kind of 3 different types. This one is going to be similar to the bridge structure that you're analyzing in the lab. So the 2 spans of the bridge are basically both simply supported. And this one more closely resembles the overhang at Leamy Hall. So that kind of canopy, that concrete canopy, and that's that kind of beam. So they're both beams, whether you know it or didn't recognize it at first, but that's what they are. Similarly, the grate, you're analyzing the grate. The grate is made up of a series of simply supported beams, and those steel plates that stop the car from falling into the drain, those are also simply supported beams. So what we're interested in is to make sure that when we design a structure with a beam in it, that beam can support the forces and moments that it's subjected to, and the material is up to the job. So to do that, we're interested in how the forces and moments distribute throughout the material. So good old faithful shear forces and moments are what we're interested in, and how they actually spread out throughout the material. So here, for example, I've got a simply supported beam with 2 supports at the end. I've got 2 point loads, P1 and P2, and then I've got a uniform load. Could be snow, could be water, could be extra concrete or something, bags of sand or something that's put on this beam here, and that's a uniformly distributed load. Point load could be basically an individual standing there. Even though they are actually spread out a little bit on the surface, we can consider them to be a point load. So to find the shear force and moments throughout this, the way we do it is we would pick an arbitrary plane, slice through it, and we want to know what's going on that plane. And the way we do it is when we slice through these arbitrary planes at different points, we actually look at as if it's a separate body. It literally has been cut, and then what would we have to do to keep that part of the beam in equilibrium? So we could find the forces and the moments that are required. Once we cut this with a chainsaw or something, we slice this beam, what would we then have to do to keep it in equilibrium? And obviously those forces and moments that we would have to provide, in reality, are provided by the other part of the beam. So that's how we do it. We virtually slice this, find out what we would have to do, and then that's the forces and moments that are actually provided by the material. So picking an arbitrary plane, this CD plane, I could slice through that. I could redraw now the section that I've sliced off. So I can look at the left-hand section here. I've obviously got my left support. I've got my force P1. And then I've got the surface here that's providing a moment and a shear force. And the convention is, when we're looking from left to right on the section, the moment is, by convention, is positive when it's anti-clockwise, and the shear force is positive when it's down, vertically down. Obviously this section we've sliced, there's another section on the other side, which if we were to draw that, which I've done here, same deal applies. We have this beam that now has to be supported because we've cut it effectively. We would have to provide a shear force and a moment, and convention is, when we go from right to left, that the shear force is positive up and the moment is positive clockwise. Obviously they're equal and opposite to what we found on the left hand side, because that's what we need for equilibrium. Newton's second law, equal and opposite. So, anyway, right, so moving on, what actually happens at the surface, I've just done a little sketch here. The shear force is obviously along the plane, it's in the plane and parallel to the plane. That force is spread over that plane. So the stress, the shear stress we call it, is spread over that plane. To generate a moment, we have forces that act perpendicular to that plane, and to get that moment they actually act in a way like this. So for this one here, if we were to provide that moment shown, that m plus, we would need forces acting in two different directions to give us the couple. Those forces would be a max at the surface of the material, and then they would diminish slowly to zero, not necessarily in the mid-axis, but what we call the neutral axis. And these stresses over these areas are what we call the shear stresses due to the bending moment. That's what's actually happening in the material. So we have these normal stresses, they're called, and then we have the shear stresses along the surface, and the two of those combine, and we'll talk about those more later in the course. So we're interested in shear forces and moments. They vary with position x, so it's useful to actually find how these forces vary and plot them on a graph, and then we can use those to find maximum minimums and actually design the beam. So let's look at a little simple example here. We've got a simply supported beam, 6 foot long, supported at both ends, and there's 300 pounds 2 inches from the right hand side. So we want to find out how the shear force and bending moment vary through this beam. So the first thing you've got to do is treat the whole thing as a free body and find the reactions R1 and R2. So just like we did before, resolve vertically, horizontally, and take moments. So in this case, we resolve vertically. We have R1 acting vertically plus R2 acting vertically up equals the 300 pounds acting down. Okay. Resolve horizontally, we don't get any information, so that doesn't help us. So next we're going to take moments. You can take moments about anywhere. Best to take it about one of the unknowns to eliminate it. So if we take moments about R1, is the obvious one, then we have clockwise 4 times 300 is balanced by anti-clockwise is the 4 plus the 2, the 6 times R2 acting in the anti-clockwise direction. So 4 times 300 minus 6 times R2 equals 0. We can solve directly for R2 to get 200 pounds. Plug that back into the first vertical force equation here, and we get R1 as 100 pounds. So usually pretty straightforward. Solve for all your reactions. Next, we're going to find out how the force, shear force, and bending moment vary throughout the beam. So starting from the left, just because we can, I'll set that as x equals 0, and then I'm going to get x increasing from left to right. So I'm going to start to look at what happens with x all the way up to the first kind of discrete change, which is where this point force 300 pounds acts. So from 0 to 4, nothing's really happening apart from the beams getting longer. So I'm going to do the analysis for that, cut some arbitrary point at x, and draw my cut section. So I've got this section here. I've got my R1 going to x where it's arbitrarily cut. For this part of the beam to be in equilibrium, vertically forces must be balanced. So R1 must equal V1. So I've got straight away, I've got the shear force is simply 100 pounds. And now for the moment, I'm going to take moments about the end because I want to find R1. So taking moments about the end where I've made the cut, I have M1 anti-clockwise equals R1 times x clockwise. So the moment M equals R1 times x equals 100x. So I can now plot the moment as a function of x going from 0 to 4. We'll do that in a minute. So the next part is to look at the beam for the second part, and we're going to continue by moving x further. We could always look at it from right to left, 1 minus x, or 6 minus x. There's a number of ways of doing it, but just for consistency, we're going to keep on going. So I draw my free body again. So now I've extended x. X is from 4 all the way up to the end of 6. So I draw my beam with my arbitrary cut, and now I do the same thing again. So resolving vertically, I have acting upwards, R1 is the only thing, and that R1 is going to be equal to the 300 acting down plus the V acting down. So 300 plus V equals R1, which implies that my shear force V equals R1 minus 300. And we already know that R1 is 100. We solved for that already. So therefore my shear force is minus 200. Okay, so now for the moments, taking moments about this point, I have my moment, which is acting anti-clockwise, minus my R1 times x clockwise, plus my 300 times x minus 4 anti-clockwise. So that's what this equation is. M minus R1x plus 300 times x minus 4 equals 0. Combine my like terms, solve for m. M equals 100x. So that's the 300 minus the R1, which is the 100x, or 100x minus 300x, and plus 3 times 4, 1200. So that's this equation here. So m equals 1200 minus 200 times x. So I've got my m now also as a function of x, and my v. So I have all the information now to plot my shear force and my bending moment as a function of x. So here we go. So from 0 to 4, shear force is simply 100. And then from 4 to 6, the shear force drops to minus 200. So that's the shear force diagram for this beam. The moment, it starts off, excuse me, it starts off as 100 times x. So as x increases, it keeps on increasing until it gets to the 4, so it's 400. And then once we get to x equal to 400, we can look at the second equation. 4 times 200 is 800. 800 from 12 is 400, which is the same point because it should be continuous. So we go from the 400, and then it's going to slope down at twice the gradient minus 200x, bringing us back to 0. So some things to note. The moment of a simply supported beam has got to be 0 at the ends, because you can't apply a moment around a pivot point effectively. And it's a continuous curve. Other things to note is that the slope of this moment curve equals the shear force. So if I look at the gradient of this curve, so if I differentiate this the first equation, so I go back from my first solution here, m is 100x. If I differentiate that with respect to x, 100x gives me 100, which is the shear force. Similarly for the second one, if I differentiate the moment, so I've got 100x, 1200 minus 200x, if I differentiate that, the slope is minus to 200, which is the slope there. So, number of things. Moments of simply supported beams are 0, curves are continuous, and the gradient of the moment curve is the shear force diagram. So some useful checks to make sure you're doing things right. And again, this only works if you stick to the sign convention, which is when you're going from left to right, shear force is positive down, moment is positive anti-clockwise. Okay, and then if you were to come from the right to left, it would be in the opposite direction. Okay, so with that said, I'm going to stop for this example, and the lecture 2 in this series, lecture 2b, will be another more comprehensive example.